Hello, everyone. Good afternoon. I'm Hyuk-Jin Kwon. I developed the Spark core, or the Apache Spark itself. I'm doing the tech lead in PySpark team. I'm also the top contributor in Apache Spark.
Hello, everyone. I'm Ruifeng Zheng. I'm also working in the open source PySpark team at Databricks. I'm one of the top contributor and is a Spark committer. I mainly worked on the PySpark, pandas API, MLlib, and so on.
All right, so today we're going to talk about the Python with Spark-connect. So the Spark community is putting a lot of effort into this, and then we're developing this very hard. So I'm very excited to talk about this here today. All right, so firstly, I'll just briefly go through the overview of the Spark-connect itself. I mean, I know we talked about this a lot here and there, but I mean, I'll just talk a little bit, a bit of background. And then the brief one will talk about the actual Python Spark client implementation, how to use it, I mean, and then there's some details. And next is that I will talk about the what's next in the Spark 3.4, like what's beyond like Spark 3.4. With the Python PySpark focus. All right, so before I talk about the overview in Spark-connect, let's start with the problem that the Spark-connect actually addresses. So this is the typical Spark cluster. So you submit the application to the Spark cluster, and then your driver lives together with your Spark cluster, and then the driver will schedule and then run some task. And then it's usually very connected and then coupled to the Spark cluster in the data center. And then why is that? You just zoom in and then you will see the Spark driver like this. And then the Spark driver actually does a lot of things. So it has of course, your application logic, and then it does have the catalyst optimizer. So it optimizes the SQL, the operations. And then, yes, it has a scheduler. So it dispatches the task, serialized, deserialized, and then send the task to the cluster. And then the worker node will execute them. And then there are listeners as well. So the event listeners, so post-hoc or pre-hoc before executing your task, then it does handle some event like this. One moment, what's wrong with you? One moment. Excuse me? Okay. All right, I think I'll have to restart the talk. I think it's good.
You want to make it full screen on the other side?
It's okay. Yeah, sorry about a bit of interruptions. All right, so your Spark driver does a lot of things. It has listeners, and it's pretty heavy. So, I mean, usually in the server has a good CPU, many CPU, and the memory, right? So you need those resources to use in a good machine. And this kind of heavy driver doesn't actually address the many modern use cases right now. For instance, the Spark nowadays, we leverage the power of data by using Spark in interactive shell or like IDE. But since your driver is in the cluster, you cannot really interactively do something. The typical use case does not cover this. And then the other applications, for instance, to use Spark, sometimes you have to change your language, right? Because your existing program is, for instance, written in Go or Node.js, but since Spark doesn't support a bit of language, so sometimes you have to switch the language of your main project. And then edge devices, IoT devices or like Raspberry Pi or your iPad. Since the driver is pretty heavy and it does a lot of things, you cannot really run on those like lightweight device. All right, so how do we handle today? For those, yes, we have the distributor server, so people can remotely execute some jobs like JDBC, or you can send the codes as string. For instance, you can leverage the Apache Libby. But it sends the codes in string, right? So you cannot really debug line by line, or like you want to debug just like you debug your regular Python local program, but it is not really possible right now. And then other language supports too. Yes, I know there are third-party library that other languages support, but they have to implement their own way to communicate with JVM. So it's pretty messy, and then it's pretty difficult at a new language, and there's no standard as well. If you take a look more closely, then you have other set of problems. So for instance, out of memory, let's say you're sharing your for instance, running the distributor server, but let's say the distributor suddenly could die out of memory, right? Then other clients are all affected. So it's a bit, you want to kill other clients, then you just make out of memory in the driver. It's a bit funny, right? And then there are dependency conflicts. Like the most common problem is that the Guava version, so like you have to deal with the exclude or shade or your dependencies in your applications, and upgradability as well. Let's say you want to upgrade the Spark cluster, right? And then usually you have to upgrade your driver side together, meaning that in your organization, like you want to upgrade your Spark, right? And then you have to just shut down everything and then upgrade all together, which is not really possible in many cases. Debuggability as well, since you cannot really line by line debug, and then observability as well, since your driver is running in your cluster, so it's difficult to add, for instance, leverage the logging system. So Spark came out, the pyspark-connect came out to address those problems. Pyspark-connect is lightweight, thin layer that basically requests, and then it decouples the Spark driver. Like it's very thin library that it decouples all the computation that happens in the driver to the cluster. So with this thin library, you can do the line by line debug, or since it defines a protocol that other language can easily implement, other language support can be very easily added to. And yes, it does address the other problems that I just mentioned about out of memory. The out of memory will only happen within your client side, so it doesn't kill the driver. And yes, it also addresses the dependency conflict because the API itself is this very thin API layer. I will talk about this a bit later, but what it does is it just construct the message and then just send the request, and that's it. And upgradability as well. So you can just upgrade the server alone, then all the client side doesn't have to change anything because it does keep the backward compatibility. So you will leverage all the improvement, the server, like the Spark side improvement, just by upgrading the server side alone. Debuggability as well, since now you can do the line by line debug. I have a bit of an example later, so I will show you. And then observability as well, because at the client side, you can, for instance, add some logins, and then you can see what's going on, because the client side doesn't need to run in the cluster side anymore. I will a little bit talk about like how it's implemented, the pyspark-connect, the library itself. So as you guys might know, the DataFrame API and then the SQL, they all share the same SQL module, right? So, and then this SQL module is basically a bunch of the logical plan and expressions. So what it does in the pyspark-connect client is that we create the one-to-one map to the logical plan, and then we define the protocol definition, and then at the client side, you constructed the protocol message, and then you just send to the server side. and then the server side will generate logical plan from the protocol definition. So this is just what all this client library does. So you send the request to the server, and then the data will be collected to the server side in arrow format. All right, so what's supported and unsupported? As I just briefly mentioned just now, in Spark, we have 3 API, right? The RDD and DataFrame and dataset. And then now we believe that the DataFrame and dataset can replace most of the RDD use cases. So, and then this DataFrame and dataset API, since we're leveraging the same SQL model, right? So we can optimize because we know the schema and then we know the column name. So we can, for instance, predicate push it down, something like that. So we want to focus on these 2 declarative API set, so users can more, user application will be more automatically optimized. So the RDD is not supported in Spark-Connect. But we will focus on the data frame and dataset in Spark 2.4. Most of API are already implemented, and that, of course, include the Python UDF and pandas UDF. And the other supports will be done in, I think, 3.5. All right, so this is the example I mentioned. So you can just add the breakpoint, and then you can see what's going on inside. Like, you can see the column names, and then you can, for instance, now execute a job here, or like you can see the schema, and then I would like to execute a job here, like during the debug, but all the computation is happening in the client side. Here, I'm just making the request. So for instance, like execute the count, ta-da, yes. All right, so that was the overview of the Spark Connect. And then the Griffin will continue to explain about the details and implementation of Python Spark client.
Thanks, QK. We now understand the overall structure of Spark Connect. Let's dive into the details and discuss how we can support it using Python. Specifically, we will focus on the Python client. Let's explore how to interact with the Python client. First, we need to launch the Connect server. We provide a script named start Connect server to accomplish it. It utilizes the Python plugin mechanism to initiate the the Spark Connect server as a Java plugin. Then on the client side, we can establish a connection to the server using the standard command pyspark along with the specified server location. For the developers who are seeking to perform local testing, we can use the local start location. This will automatically initiate a local Connect server and then establish a connection to it. For scenarios which requires programmatic access, we can use the new session API, the remote method, to connect to an existing server. The following is a notebook example that demonstrates how to use Spark Connect to build applications. The notebook will walk you through each of those steps. First, we launch the Spark Connect server with the provided script. Then on the client side, we connect to the launched server with the remote method. After the connection is established, we can start to process the data. In this example, we create a data frame from the local data set. You can also use data loader to load some data from the data source. After your processing, we can save the result to somewhere. For example, we can display this data frame. We use the data frame.show method to print the first rows of the data frame. The communication between the client side and the server side are all based on the protobuf messages. Those messages carry various types of data, including the logical plans, circle commands, expressions, data types, configurations, and more. Consider the Spark.circle method as an example. The circle query string and its parameters are packaged into a protobuf message on the client side, and then it will be sent to the server side via gRPC. We use the buff tool in this project to manage the protobuf schemas and code generation, as well as to check the link and detect the potential breaking changes. For static functions, we have implemented a Python decorator that verifies if the current Spark session is a remote Spark session. If the current session is indeed remote, the decorator will trigger the execution of the new implementations. For instance, in the new function APIs, vanilla PySpark session would typically invoke the JVM side with a py4j to fetch the result expression. This expression is normally resolved. However, in the case of a remote session, the decorator ensures that the unresolved expressions are constructed on the client side, and then it will be sent to the server side, instead of directly invoking the JVM side. This decorator also enables us to reuse the namespace in the Spark-connect. For each instance in the vanilla PySpark, we create a corresponding instance in the Python client. We then use the decorate to route those invocations to the appropriate Spark-connect APIs. In addition to reusing the namespace, we also reuse all the tests. It includes both the unit tests and the doc tests. For unit tests, we transition the actual test classes to mixed-in classes. And in the vanilla PySpark, we initiate a regular session for testing. However, in the Python client, we initiate a local remote session instead. For doc tests, it is similar. We have the connect APIs duplicate all the doc string from the vanilla PySpark. We then execute the doc tests also with a local remote session. Then let's talk about the how to manage the dependency. Managing dependency in an application can be quite difficult and complex in a distributed environment. This complexity arises from the difficulty in ensuring that all nodes in the environment have the desired setup. Occasionally, environment pollutions occurs, which refers to the situation where the unwanted or conflicting dependencies exist in the same environment. In Spark 3.1, comprehensive support for dependency management was introduced as a part of Project Zen. This feature is designed to work with three popular Python package management systems. They are Conda, Virtual Env, and PEX. Let's dive into the Conda example for a better understanding. Python users can utilize a Conda environment to distribute their third-party Python packages. This is achieved by using the conda pack command, which packages the environment for distribution. Once the environment is packed, it can be shipped along with the scripts. This allows the packaged environment to be included in the Spark job submission. This archive is then automatically unpacked on the executors, ensuring that all the nodes have the necessary dependency to execute the job. This feature simplifies the dependency management in a distributed computing environment, reducing the risk of environment pollution. In Spark Connect, dependency management becomes more difficult and complex. This is because the Connect server is long alive, and there can be many applications, many connections in the same time, and each one can have its own Python version, dependencies, and environment. The proposed solution is to support the session-based archives In this setup, each session has its own dedicated directory where all related Python files and archives are stored in it. When Python workers are excluded, the current working directory is set to its dedicated directory. This ensures that each session has access to its specific set of dependency and environment, thereby mitigating potential conflicts. Another enhancement in Spark-connect is the support for dynamic dependency management. This feature is particularly important and beneficial during the development of workloads where the dependency might need to be adjusted frequently. For instance, a developer might want to test the impact of using a different version of a specific library. To utilize this feature, the user can simply package the new environment and specify the new environment via Spark's runtime configuration. During runtime, the dependency manager will replace the corresponding directory with the new environment. This allows any new task to automatically switch to the new environment, facilitating seamless transition between the different sets of dependencies. This feature in Spark-connect is also compatible with virtual env and PEGs. In Spark 3.4, a new module named the Torch distributor has been introduced in PySpark. This module is designed to facilitate distributed training using the PyTorch library on Spark-connect, on Spark clusters. This feature is versatile and can support both PyTorch functions and PyTorch scripts. Initially, this module set up the environment and established the communication channels between all the workloads. It uses the CLI command to exclude the distributed training across those workloads. In the 3.5, we have made the PyTorch distributor compatible with the Spark-connect. This compatibility is achieved by replacing the RDD implementation with the Spark-connect DataFrame APIs. Specifically, we have modified the mapping pandas and the mapping arrow method to support the barrier mode. This modification is necessary because there isn't a DataFrame API corresponding to the RDD barrier instance. The barrier mode is used to train the PyTorch mode within its barrier UDF, and after the training, the model coefficients are connected and sent back to the driver side. To enhance performance, we also implemented a split combine strategy. This strategy is designed to better utilize the streaming connection feature already available in the Spark-connect. Okay.
Thanks, Rufen. All right, so we talked about the implementation to Spark-connect 3.4. And then what's next, what's coming in Spark-connect. And I'll talk a little bit about the what's next and what's going on. Some of them are actually a bit controversial in discussion, so just take it as just something, it's not finalized topics. All right, so we will provide the complete Python API coverage, right? So on the roadmap, actually most of them are already done, but the SQL, yes, supported, and structured streaming, yes, supported, able or other functions, and the pandas API on Spark is also supported from 3.4, 3.5, and then we are also focusing on providing the same API layer with the latest pandas. The ML support is also done, and then the Spark Summit is in progress, but it has a bit of controversial or something in this, like we need to discuss, so it's not finalized yet. And then, yes, we already support the PySpark shell. As I just mentioned, we are explicitly not supporting the RDD API, and then the resource API too, that server concept, because it supports the GPU and then it sets the resource to use during the shuffle. So this is kind of a server concept. So we don't support. And then dstream is deprecated officially, so we don't plan to add this. All right. This is still in discussion, but roughly, we are thinking about making the pyspark-connect to use by default, meaning that if you don't specify anything, then when you use the higher Spark version, for instance, Spark 4, then it will use the pyspark-connect under the hood automatically. And then we're thinking about introducing two concepts. So first is driver that that was like master that we used before. So you specify the Spark cluster, then it will not use pyspark-connect. If you specify the remote, then it will use the pyspark-connect server explicitly. And if you don't specify anything, then it will run the pyspark-connect server locally, and then you will use it automatically. Again, this is still in discussion, but this is what we are thinking right now. This is also very interesting stuff. So we're thinking about introducing the pure Python packaging. So for now, 3.4, yes, we have the pyspark-connect, but you still have to download the 3 MB the jars together. If you do pip install PySpark, then it's a bit heavy, right? So we are thinking about introducing the pure Python package, meaning that the Python would just be this Python connect library will be very lightweight and small. And then with this pyspark-connect pure Python package, it will only support the pyspark-connect. And then if you pip install PySpark, then it will support non-pyspark-connect and then pyspark-connect together. This is also planned. It's not finalized yet because it does introduce a lot of breaking change, right? So we're still discussing. Arrow optimized Python UDF. So this is actually not only the pyspark-connect, but in PySpark itself. So we're thinking about optimizing the regular Python UDF to use the arrow to allow the vectorization during serialization and deserialization. We already actually almost implemented, but there is a bit of problem about the type coercion, because the current type coercion in the regular Python UDF is not very well defined. For instance, sometimes if the return type is not matched with the provided SQL type, then sometimes it just returns some weird Java class string. So we are thinking about standard making this behavior more consistent, coherent with the standard with using the arrow vectorization. I did the rough benchmark. You will have a 3 times to 5 times faster Python UDF with this. Feature parity. So I was in the AMA session just now, and then somebody asked why Python has less feature compared to Scala or SQL, or why is it slow? We are focusing on Python right now, so we will have it exactly same, or actually more than the Scala or SQL. We will have more features in Python now, and then we will always have the same feature in the Python side. In 3.5, we will add all the functions, all SQL functions that are available in SQL, but some were not in Python or Scala side before. We will add all the functions, and then we will also add some API, for instance, for subquery. With DataFrame, you cannot do it right now, right? But we will add a API, and then we will have a exact feature parity. UDTF is one nice thing too. Now, in 3.5, you will be able to define user-defined table function, meaning that this is very useful. For instance, it can define your own table-wise operation, and then it generates some rows. So you can leverage this, for instance, in ML, and then you can use it together with lateral join, or even you can use it for writing your own custom data source. And then as you can see at the bottom, you can register the table function, and then you can invoke in the SQL side. So you can define your own function UDF, and then you register it, and then you can use SQL, or you can use in other languages even. We don't support the permanent UDF yet, UDFTF yet, but we are working on it. All right, there's another interesting about the XGBoost and then the Spark-connect ML. Riven has a better insight in ML side, so he will briefly talk about this slide.
For ML, we are not simply migrating the existing ML lib to the Spark-connect. Instead, we will leverage this opportunity, this chance to better integrate with the popular machine learning frameworks. We have already supported the PyTorch distributor, and XGBoost is a leading framework to work with the standard tabular data. For example, this type of data is stored in pandas data frames. We plan to also support the XGBoost distributor to distribute it training workloads. And after we ship the PyTorch distributor in 3.4, we are going to implement the Spark-connect ML on top of the PyTorch to support more traditional algorithms. For example, we will support the classic logistic regression. The new Spark-connect ML will be released in 3.5. Okay.
All right, thanks. All right, so this leads me to the end of the talk. This is the release timeline we saw. So in Spark 1.0, we focused on the Spark SQL and PySpark. And then 2 years later, structured streaming came out, whole stage code gen came out, and then we did a bit of Tungsten project to optimize the shuffle speed. And then 4 years later, Spark 3.0 came out. And then here we focused on Python usability. We initiated Project Zen, and we improved a lot of usability in Python side. We introduced the pandas API on Spark with visualization, AQE, and the DPP. There are techniques for SQL. And then now, 4 years later, we're thinking about a Spark 4.0 that focuses on Spark-connect that I just mentioned now, and then a bunch of LLM and other talks. So of course, it's not decided yet. We just started the discussion, but I think we can expect the Spark 4.0 probably next year. All right, so that's all I prepared. If you have any question, I'm happy to answer.